The transport truck rattled along the Michigan highway, its canvas cover flapping in the October wind of 1944. Inside, 5 German engineers sat in silence, their hands unbound, but their spirits shackled by the weight of capture. Hauptmann Friedrich Weber, 42 years old with silver threading through his dark hair, stared at the metal floor between his boots. 3 weeks ago, he had been overseeing production at the Daimler-Benz plant in Stuttgart. Now he wore the coarse grey uniform of a prisoner of war, being driven to God knows where in the American heartland. Across from him sat Klaus Richter, younger by a decade but no less accomplished. Klaus had worked on the DB601 engines that powered the Messerschmitt fighters, engines that represented the pinnacle of German engineering precision. His face wore the same expression it had carried since their capture near the Ruhr Valley, defiant superiority, poorly masked by exhaustion. "They're taking us to some factory," Klaus muttered in German, his voice barely audible over the truck's grinding transmission. "Probably want us to see their assembly lines. Show off their production numbers." Friedrich didn't respond immediately. He'd learned in his 2 decades of engineering that silence often revealed more than words. The American guards flanking them didn't speak German, or pretended not to. They were young men, probably farm boys from Iowa or Nebraska, with that peculiar mix of friendliness and vigilance that seemed uniquely American. The truck slowed, turning through a gate where armed guards checked papers. Through a gap in the canvas, Friedrich caught glimpses of vast industrial buildings, their roofs stretching like metal horizons under the grey autumn sky. Smokestacks punctured the clouds, and even through the canvas, he could hear the distant thunder of machinery, a sound he knew intimately, the heartbeat of production. They were led into a concrete building, sterile and functional in that American way that eschewed the architectural grandeur Friedrich associated with German industrial facilities. A colonel waited in a spare office, flanked by 2 men in civilian clothes who had the calculating eyes of engineers. The colonel's nameplate read Morrison, and his weathered face suggested he'd seen combat before being reassigned to whatever this posting entailed. "Gentlemen," Colonel Morrison began in English, which all 5 German engineers understood to varying degrees. Friedrich's English was fluent, cultivated during a pre-war exchange program at MIT that now felt like it had happened in another lifetime. "You're here because we believe in mutual understanding. You're going to see some things today. What you see stays in your heads until this war is over. Is that clear?" Friedrich translated for those whose English was weaker, though the meaning was plain enough. They were about to be shown something, either as a form of psychological warfare or because the Americans genuinely believed the war was near enough to its end that such knowledge wouldn't matter. One of the civilian engineers, a man named Patterson, with oil stains on his sleeves that marked him as someone who actually worked with his hands, led them through a series of corridors. The smell hit Friedrich first: machine oil, hot metal, that distinctive ozone scent of electrical systems under load. It was familiar and foreign at once, the dialect of industry spoken with an American accent. They emerged onto an observation platform overlooking an assembly floor the size of a city block. Friedrich's breath caught despite himself. Below, hundreds of workers moved in choreographed precision along assembly lines that stretched beyond his line of sight. But it wasn't the scale that struck him. German factories could be massive. It was the method. Every station had identical tools, identical parts, identical procedures. It was mass production refined to a degree that made even his experienced eye widen slightly. "This is our tank engine facility," Patterson explained, his voice carrying the pride of a craftsman, but none of the pomposity Friedrich expected. "We produce complete power plants for the M4 Sherman. Current output is about 1,200 units per month." Klaus scoffed beside him, unable to contain himself. 1,200, he said in German, then switched to halting English. "Quantity over quality. This is what happens when accountants design war machines." Patterson's expression didn't change, but Friedrich caught the slight tightening around his eyes. The American engineer had understood the insult perfectly. Instead of responding with anger, Patterson smiled slightly. "Follow me, gentlemen. There's something else I think you'll find interesting." They walked through corridors where the sounds of production echoed like distant artillery. Friedrich found himself analyzing everything. The lighting, brighter and more uniform than German factories. The cleanliness, almost surgical. The workers, many of them women moving with practiced efficiency. In Germany, engineering was treated as an almost mystical pursuit, the domain of masters and apprentices. Here it seemed democratized, broken down into steps simple enough that anyone with training could participate. It should have felt crude. Instead, it felt disturbingly effective. The next building they entered was different. The main floor was dominated not by assembly lines, but by testing bays, massive chambers where engines could be mounted and run under controlled conditions. The noise here was deafening, a mechanical roar that made conversation impossible without shouting. Patterson led them to a glassed-in observation room where the sound dampened to a tolerable thunder. "Before we go further," Patterson said, his tone shifting to something more serious, "I want to show you something. This is a standard American radial engine. 9 cylinders, air-cooled, used in everything from our fighters to transport aircraft. On a test stand visible through the thick glass, a radial engine spun, its cylinders arranged in a circular pattern around the crankshaft." Friedrich examined it with professional interest. The design was familiar. Radial engines had been around since the First World War. This one appeared compact, well-machined, but nothing revolutionary. Beside him, Klaus actually laughed. "This is what you wanted to show us?" Klaus said, his English improving with his contempt. "We abandoned radial designs for high-performance applications years ago. Too much drag, too little power for the weight. Our inline engines are far superior." Friedrich wanted to caution his colleague, but technically Klaus wasn't wrong. The German DB605 engines that powered their late-war fighters produced over 1,800 horsepower from inline configurations that were marvels of precision engineering. American radial engines, by comparison, seemed almost primitive in their simplicity. Patterson nodded as if he'd expected exactly this response. "You're right about the individual unit performance. Your DB engines are magnificent pieces of engineering. Absolutely magnificent." He paused, and Friedrich caught something in that pause, a setup. "But let me ask you something. How long does it take to manufacture one of your DB605 engines, from raw materials to a completed tested unit?" Klaus hesitated. Friedrich knew the answer. Approximately 200 man-hours for a single engine, with tolerances measured in microns and components that required skilled craftsmen to produce. "It depends on many factors," Klaus said defensively. "Quality cannot be rushed. Our Pratt & Whitney R2800 radial," Patterson continued, gesturing to the engine on the test stand, "takes about 400 man-hours to produce. It generates 2,000 horsepower reliably. It can take battle damage that would destroy an inline engine, and we can train someone to maintain it in a matter of weeks instead of months. More importantly, we're currently producing them at a rate of about 200 per day." The number hung in the air like a physical presence. 200 engines per day. Friedrich did the mathematics almost unconsciously. 6,000 per month, 72,000 per year. Even accounting for American exaggeration, the implications were staggering. "Impossible," Klaus said, but his voice had lost its certainty. "Come with me," Patterson said quietly. They walked deeper into the facility, through corridors where the air smelled of paint and fuel. Friedrich noticed details. The pipes color-coded for different fluids, the electrical systems standardized and modular, the way tools were organized at every workstation identically. It was engineering philosophy made manifest. Reduce complexity, standardize everything, eliminate variability. The room Patterson led them into was enormous, a cathedral of American industrial power. The ceiling soared 40 feet high, supported by steel trusses that could have carried locomotives. But what dominated the space was the machine in the center, a massive testing platform holding what appeared to be multiple engines mounted together, their crankshafts synchronized through a complex arrangement of gears and linkages. Friedrich stopped, his engineer's mind struggling to process what he was seeing. It wasn't one engine. It wasn't even two. 4 complete radial engines arranged in an X pattern, their power outputs feeding into a central transmission. The scale was unprecedented, but more than that, it was the audacity of the concept that struck him. "We call it the Chrysler A57 Multibank," Patterson said, and for the first time Friedrich heard genuine enthusiasm in the American's voice. 30 cylinders, 425 horsepower total, per engine. Combined output when synchronized, around 1,700 horsepower, but that's not the point. The point is that we built this from 5 standard automotive engines. Chrysler straight sixes, the kind of engine that goes into taxis and delivery trucks. Klaus was shaking his head, but Friedrich could see the disbelief warring with fascination on his colleague's face. That's completely impractical. The synchronization alone would be a nightmare. The vibration harmonics, the thermal management, the maintenance requirements, all solved, Patterson said simply. Is it elegant? No. Is it the most efficient design possible? Absolutely not. But here's what it is. It's practical, it's producible, and it works. When one engine needs maintenance, we can access it without disassembling the entire unit. When we need more power, we add another bank. When production is constrained on one component, we can substitute from different supplier chains. It's engineering for mass production and field maintenance, not for theoretical perfection. Friedrich moved closer to the observation glass, his eyes tracing the connections, the cooling systems, the electrical harnesses. It was ugly in the way a bulldog was ugly, purposeful, functional, unapologetic. German engineering pursued elegance. This pursued effectiveness. He wasn't sure which approach disturbed him more. A technician on the floor below signaled to Patterson, who nodded and pressed an intercom button. "Gentlemen, they're about to run a full power test. You might want to hold on to something." The warning made Friedrich grip the railing instinctively. Through the glass, he watched technicians clear the area, their movements practiced and efficient. Warning lights flashed. Then, with a roar that made the earlier engine noise seem like a whisper, the multibank came to life. The sound was apocalyptic. 30 cylinders firing in synchronized chaos, their combined exhaust creating a visible shockwave in the air. The test stand, massive as it was, vibrated under the load. Friedrich felt the vibration through the floor, through the railing, through his bones, but the engine held together, the crankshaft spinning in harmony. Power meters climbing steadily. "We're at 75% power now," Patterson shouted over the noise. "In actual operation, we rarely run them above 80% to ensure longevity. But watch this." He signaled again, and the technicians adjusted throttles. The roar intensified, became something almost physical. The power meters climbed. 500 horsepower, 1600, 1700. At 1800 horsepower, Patterson signaled to hold. The engine ran at that output for 30 seconds that felt like minutes, steady and unrelenting. Then the technicians began shutdown procedures, and the thunder gradually subsided to a growl, then silence. In the quiet that followed, Friedrich realized his hands were shaking slightly, not from fear, but from the realization of what he'd just witnessed. This wasn't about one engine. It was about a philosophy of war production that Germany had fundamentally misunderstood. "How many of these have you built?" Friedrich asked, his voice hoarse. Patterson looked at him directly. "That information is classified, but I can tell you that this is one of multiple approaches we're taking to vehicle power plants. We have factories producing Sherman tank engines, Liberty aircraft engines, GMC diesel engines for trucks, marine diesels for landing craft, all using similar principles: standardization, parts interchangeability, simplified maintenance." Klaus had been silent during the test, and when Friedrich looked at him, he saw a man whose worldview was crumbling. "You're building thousands," Klaus said softly. "Tens of thousands. We're building what we need," Patterson replied. "And gentlemen, if you're honest with yourselves, you know what that means for the outcome of this war." They were led to a mess hall after that, given surprisingly decent coffee and sandwiches. The 5 German engineers sat together at one table, speaking in low voices while American personnel moved around them, some curious, most simply going about their business. "It's quantity warfare," Klaus said, still trying to hold on to his convictions. "They're flooding the battlefield with inferior equipment. Individual German tanks are superior. Our aircraft are faster, more agile. And there are 10 American machines for every one of ours," Friedrich interrupted quietly. He stared into his coffee, seeing patterns in the dark liquid. "Klaus, listen to me. I've been doing this for 20 years. I helped design engines that were masterpieces of precision. Do you know how long it takes to machine a crankshaft for a DB605 to the required tolerances? Do you know how many skilled workers it requires? How many specialized tools? Quality matters," Klaus insisted, but his voice was uncertain. "Quality matters when you're building race cars," Friedrich said, feeling something break inside him, some certainty he'd carried his entire professional life. "In war, mathematics matters more. If they can put 10 serviceable tanks in the field for every excellent tank we produce, they win. If they can replace their losses faster than we can inflict them, they win. And that's exactly what they're doing. One of the other engineers, a quiet man named Ernst who'd worked on U-boat engines, spoke up. I saw the workers, he said. Many of them women, young people. They're not master craftsmen. They're trained for specific tasks, simple tasks. But they do them with incredible consistency. It's an insult to the profession, Klaus said, but he sounded lost rather than angry. It's the future of the profession, Friedrich corrected gently. We've been building Ferraris while they've been building Volkswagens. Except they're building millions of Volkswagens and they all work. The afternoon brought more revelations. Patterson, perhaps sensing that the shock was wearing off or perhaps following some predetermined script, led them to another facility. This one produced aircraft engines, and the scale made the previous factory seem almost quaint. The assembly line stretched for what must have been half a mile, with engines at various stages of completion, moving along an overhead track. This is our Pratt & Whitney plant, Patterson explained. We're currently producing about 6,000 engines per month here. This is one of 4 such facilities in the country. Friedrich did the mathematics again, couldn't help himself. 24,000 aircraft engines per month. In Germany, total production across all manufacturers might be approaching 5,000 per month on a good month, and that was stretching the Reich's industrial capacity to its breaking point. How? Klaus asked, and the single word contained his entire shattered worldview. Patterson seemed to consider his answer carefully. They were standing on a platform overlooking the assembly line, watching as engines moved from station to station, like patients in a surgical theater. It starts with design philosophy, he finally said. Your engineers design for maximum performance. Ours design for maximum manufacturability. A German engine might have 10,000 parts. Ours has 6,000, and 3,000 of those are identical fasteners we can produce on automatic screw machines. He pointed to a station where workers were installing cylinder heads. See that tool they're using? It's a specialized torque wrench that applies exactly the right pressure and clicks when it's done. The worker doesn't need to be a skilled mechanic who can feel the proper torque. They just need to tighten until it clicks. Same result, but we can train someone to do it in hours instead of years. But what about innovation? Klaus protested. What about improving the design, refining the performance? We do that too, Patterson said. But we do it between production runs, not during them. Once we've established a standard, we produce it in massive quantities, while engineers work on the next generation. Your approach is to constantly tweak and refine each individual unit. It makes each engine slightly better, but destroys any hope of mass production. They watched in silence as workers moved with mechanical precision. Friedrich noticed something else. The workers looked healthy. They weren't malnourished or exhausted. They worked 8-hour shifts, Patterson explained, with breaks. There were safety regulations, medical facilities on site. The concept was foreign to Friedrich, whose experience in German factories had been of increasingly desperate conditions as the war dragged on. May I ask you something? Friedrich ventured. Patterson nodded. Why are you showing us this? The war isn't over. Surely this information, if we were to escape or be exchanged, Patterson smiled without humor. First, you're not going to escape from Nebraska. Second, even if you got this information back to Germany, what would it change? You can't replicate our industrial capacity. You can't retool your entire manufacturing philosophy in the middle of a war. And third, he paused, choosing his words carefully. Third, I think some of your leadership already knows. They're just not willing to accept what it means. The words hit Friedrich like a physical blow because they rang with truth. How many reports had been filed? How many production analyses had been sent up the chain of command? He thought of Speer, the armaments minister, desperately trying to rationalize production, to find efficiencies in a system designed around craft traditions rather than industrial scale. As the afternoon wore into evening, they were shown more. A factory producing Liberty aircraft engines, another making GMC truck engines, a facility that stamped out hull armor for tanks, using presses the size of buildings. Each revelation was another hammer blow against the edifice of German industrial superiority. But it was the last stop that truly broke Klaus's spirit, and Friedrich's as well. They were led to what appeared to be a storage yard. acres of concrete covered with row after row of completed engines, each wrapped in protective coating, each tagged and ready for shipment. There were thousands of them, maybe tens of thousands, stretching to the horizon under the setting sun. "This is about 2 weeks of production," Patterson said quietly. "We're currently producing faster than we can ship. The Navy yards are the same way. We're building Liberty ships faster than we can crew them. We're manufacturing ammunition faster than we can use it. The entire American economy has been converted to war production, and it's producing at a rate that, well, you can see for yourselves." Klaus sank down to sit on a nearby crate, his face in his hands. Friedrich remained standing, but he felt hollow. In his mind, he was calculating, running the numbers, comparing German production capacity to what he'd seen today. The mathematics were brutal. Even if German engineering was superior unit for unit, which he was no longer certain was even relevant, the disparity in production was insurmountable. "We've lost," Klaus said softly in German. "Haven't we? Not just the war. The entire concept, everything we believed about engineering excellence, about precision, about craftsmanship, none of it matters against this." Friedrich wanted to contradict him, to defend the German engineering tradition that had been his life's work. But standing in that yard, surrounded by the evidence of American industrial might, he couldn't find the words. Instead, he thought about something his professor at MIT had told him years ago. Good engineering isn't about creating the best solution. It's about creating the best solution that can actually be built. That night, in the barracks where they were housed, the 5 German engineers talked late into the darkness. The guards left them alone. Where would they go? They were in the middle of America, surrounded by an industrial capacity they now understood they could never match. "What do we do when we go back?" Ernst asked. None of them doubted they would eventually return to Germany, whether as part of a prisoner exchange or at the war's end. "We tell the truth," Friedrich said firmly. "We write reports detailing everything we've seen. We explain the scale, the methods, the philosophy. We make them understand. Will they listen?" Klaus asked. He'd been quiet since their return, processing everything he'd seen. "Probably not," Friedrich admitted. "But we have to try. Maybe after the war, if there's anything left to rebuild, this knowledge will matter. We can't just return to the old ways. We have to learn from this." The next morning, Colonel Morrison met with them in a conference room. His manner was more relaxed, almost collegial. "Gentlemen, I trust yesterday was educational. You're going to remain here for the duration of the war, but you'll be treated fairly. We may occasionally ask for your technical expertise on certain matters. Your knowledge of German engineering practices could help us understand how to counter certain systems." Friedrich translated for the others, then spoke for the group. "We are prisoners of war, Colonel. We will not provide information that could harm Germany's military efforts." Morrison nodded, as if he'd expected this response. "I understand. But let me pose a hypothetical. If you knew that sharing certain technical information could shorten the war and save lives on both sides, would your position change?" The question hung in the air unanswerable. Friedrich thought about the factories he'd seen, the production capacity, the mathematical inevitability of Germany's defeat. How many would die in the months or years it took for that inevitability to play out? Over the following weeks, the 5 engineers settled into a strange routine. They were housed in relative comfort, fed adequately, even given access to technical journals and books. Sometimes American engineers would visit, ostensibly to discuss theoretical matters, but the conversations always eventually turned to practical applications. Friedrich found himself in an unexpected role, translator of not just language, but philosophy. He would explain German engineering approaches, the emphasis on precision and individual excellence, while Patterson and other American engineers would explain their own methods, the focus on reproducibility and scale. "You see it as a compromise," Patterson said during one of these discussions. They were in a small office, reviewing blueprints for a proposed improved radial engine. "Making things simpler, more producible, you think it's accepting inferior quality. Isn't it?" Friedrich challenged. Patterson shook his head. "It's accepting appropriate quality. Over-engineering is as much a flaw as under-engineering. If you design a bolt to hold 10 times the maximum load it will ever experience, you haven't made it better. You've made it unnecessarily expensive and difficult to produce. German engineering has a tradition of over-specification. because precision became equated with excellence. But excellence should be measured by whether something achieves its purpose efficiently, not by how difficult it was to make. The argument resonated with Friedrich because he'd seen the evidence. American equipment might not match German performance specifications, but it showed up in overwhelming numbers and kept functioning in conditions that would have destroyed more delicate machinery. Soldiers didn't need the theoretically best weapon. They needed weapons that worked reliably and could be replaced when damaged. Klaus, meanwhile, underwent a different transformation. Initially devastated by what he'd learned, he became almost obsessive in studying American production methods. He filled notebooks with observations, sketches, calculations. "When this is over," he told Friedrich one evening, "if there's a Germany left to rebuild, we'll need this knowledge. We can't just go back to the old ways." In January of 1945, news began filtering in about Soviet advances in the East, about Allied bombing campaigns devastating German cities, about the Battle of the Bulge's failure. The Guards didn't deliberately share information, but it was impossible to keep news entirely contained. Friedrich watched Klaus and the others absorb each piece of news with a combination of dread and resignation. One cold February morning, Patterson found Friedrich in the machine shop, where the prisoners were sometimes allowed to work on non-critical projects. Friedrich was examining a cross-section of a radial engine cylinder, studying the cooling fin's design. "I wanted to show you something," Patterson said. He led Friedrich to his office and spread out a blueprint on the desk. "This is our proposed next-generation radial engine. We're incorporating several improvements based on our observations of German designs. See this oil circulation system? That's adapted from your DB engine concepts. And this valve timing mechanism, inspired by your Junkers diesel engines." Friedrich studied the drawings with professional interest. The design was clever, maintaining American manufacturing simplicity while incorporating German refinements where they added real value. "You're not just producing," he said slowly. "You're still innovating. You haven't sacrificed that." "Of course not," Patterson replied. "The difference is we innovate in stages, standardize the improvements, then produce in volume. We don't make every engine slightly different. We make thousands of engines identical, then design the next generation incorporating lessons learned. It's slower in some ways, but it's sustainable." "And after the war?" Friedrich asked. "This production capacity doesn't just disappear." Patterson leaned back in his chair, a thoughtful expression crossing his face. "No, it doesn't. We'll probably beat our swords into plowshares, as they say. Convert tank plants to automobile production. Aircraft factories to commercial aviation. The methods will remain. The capacity will remain. The world is going to change, Friedrich. The era of handcrafted precision as the standard for industrial production is over. Mass production with controlled quality is the future." The words stung because Friedrich knew they were true. He thought about German factories, about the craftsmen who spent weeks perfecting individual engines, about the pride in that work. All of it rendered obsolete by assembly lines and interchangeable parts. "It feels like we're losing more than the war," Friedrich said quietly. "We're losing a tradition, a way of thinking about engineering." "You're not losing it," Patterson corrected gently. "You're adding to it. German engineering precision is still valuable. It just needs to be applied differently. Designed for manufacturing. Create systems that can be produced efficiently without sacrificing essential quality. That's the synthesis, Friedrich. That's what needs to be built after this war ends." In March, news came of Allied forces crossing the Rhine. In April, of Soviet forces entering Berlin. The 5 German engineers gathered each evening in their barracks, listening to what news they could glean, each processing the reality of Germany's defeat in their own way. For Friedrich, understanding had brought a strange kind of peace. He'd spent his professional life pursuing engineering excellence through precision and craftsmanship. Now he understood that excellence could take other forms. Efficiency, reproducibility, practicality. Both approaches had value. The tragedy was that it had taken a war to teach him this lesson. One evening in late April, Klaus showed Friedrich his notebooks. They were filled with detailed observations about American production methods, analysis of how those methods could be adapted to European conditions, proposals for post-war industrial reconstruction. "Look at this," Klaus said, pointing to a sketch. "A standardized engine design that could be produced in existing facilities, using simplified tooling. Not as powerful as our DB engines, but manufacturable in quantities that could rebuild transportation infrastructure. And here a modular truck design using interchangeable components across different vehicle types. Friedrich studied the drawings with growing respect. Klaus had taken the lessons of their captivity and turned them into something constructive. Not just copying American methods, but adapting them, finding ways to synthesize German precision with American practicality. You should patent these after the war, Friedrich said. If there's a functioning patent system left, Klaus shook his head, I'll publish them freely. Germany is going to need all the help it can get to rebuild. If these ideas can contribute to that, I don't need to profit from them. In early May, the news they'd been expecting finally came. Germany had surrendered. The war in Europe was over. The 5 engineers received the news in silence, each man processing the end in his own way. Relief that the killing was finished, mixed with grief for the devastation left behind, with uncertainty about what came next. Colonel Morrison met with them the following day. Gentlemen, the war is over. Your status is being reviewed. Eventually you'll be repatriated, though the process may take some time. In the meantime, we'd like to offer you an opportunity. He explained that American engineers were developing plans to help rebuild Europe's industrial capacity. German engineers with expertise would be valuable in this effort, particularly those who understood both German and American industrial methods. Think about it, Morrison said. No pressure. You've been prisoners. You have no obligation to help us. But if you're willing, your knowledge could help your country recover faster. Friedrich looked at Klaus, at Ernst, at the others. They'd been shown American industrial might as a form of psychological warfare, to break their spirit. Instead, they'd been given an education in practical engineering that might prove more valuable than any technology they'd worked on during the war. We'll help, Friedrich said, speaking for all of them, on one condition, that we're working to rebuild, not to continue the conflict through other means. Morrison smiled. That's the only reason I'm asking, Hauptmann Weber. The war's over. Now comes the harder part, winning the peace. Over the following months, the 5 German engineers worked alongside American counterparts on reconstruction plans. They analyzed Germany's remaining industrial capacity, identified what could be salvaged, proposed how American production methods could be adapted to European conditions with their different infrastructure and resources. Friedrich found himself in lengthy discussions with Patterson about modular design, about creating industrial equipment that could be maintained with limited spare parts, about training programs that could quickly develop skilled workers from a population devastated by war. In August, the war in the Pacific ended with terrifying suddenness. Friedrich heard about the atomic bombs with horror, but also with a grim understanding of the same principle he'd learned watching American engines. When you could manufacture overwhelming force, you would use it to end the conflict quickly. In September, Friedrich received news that he and the others would be repatriated within months. The process had been delayed by the chaos in post-war Germany, but arrangements were being made. He felt conflicted about returning. America had been his prison, but it had also been his school, teaching him lessons that would shape the rest of his career. On one of his last evenings at the facility, Patterson took Friedrich to a nearby bar, frequented by off-duty engineers. They sat in a corner booth, drinking American beer that Friedrich had learned to tolerate, if not enjoy. "What will you do when you get back?" Patterson asked. Friedrich considered the question. "Help rebuild if I can. Try to incorporate what I've learned here. Teach maybe if the universities are still functioning. Try to bridge 2 philosophies of engineering. You'll face resistance," Patterson warned. "People don't like having their fundamental assumptions challenged. German engineering has a proud tradition. So does American engineering," Friedrich replied. "The difference is, Americans weren't afraid to challenge their own traditions when circumstances demanded it. We need to learn that flexibility." Patterson raised his glass to flexible thinking then. And to bridges between traditions. They drank to that. 2 engineers from opposing sides of a terrible war, finding common ground in the practical realities of their profession. When Friedrich finally returned to Germany in November of 1945, the devastation shocked him, even though he'd been mentally prepared. Cities lay in ruins. Factories were shattered, the population was traumatized and starving. But he also saw resilience, people already working to rebuild from the rubble. He found Klaus in Munich, working with a provisional government agency trying to restore basic industrial capacity. Klaus's notebooks had grown thicker, filled with adapted designs and practical proposals. Together, they began teaching workshops for surviving engineers, sharing what they'd learned about mass production methods, about designing for manufacturability, about the synthesis of precision and practicality. The response was mixed. Some engineers embraced the new approaches, understanding that Germany couldn't rebuild using pre-war methods. Others resisted, seeing it as abandoning their heritage. Friedrich understood both positions. He'd wrestled with the same conflict himself, but gradually the practical advantages became undeniable. Factories rebuilt using American-inspired methods reached production faster than those trying to restore traditional approaches. Workers trained using simplified, standardized procedures became productive more quickly than those taught through traditional apprenticeships. The mathematics were as inexorable in peace as they had been in war. Years later, as Germany's economic miracle took shape and the country rebuilt itself into an industrial powerhouse, Friedrich would sometimes think about that day in Michigan when he'd watched the multibank engine run at full power. He'd gone into that facility expecting to see American engineering hubris. Instead, he'd witnessed a fundamental truth about the modern world: that excellence in engineering wasn't about creating perfect individual units, but about creating good units in quantities that could change the world. German engineering would rebuild its reputation, would become synonymous again with quality and precision. But it would be a different kind of precision, one that balanced perfection with practicality, that understood that sometimes good enough, produced in sufficient quantities, and maintained reliably, was better than perfect, produced in numbers too small to matter. The lessons learned in captivity, the humbling experience of watching American industrial might at work, became the foundation for post-war German industrial success, not because German engineers abandoned their traditions, but because they learned to adapt them, to synthesize them with other approaches, to understand that there were many paths to excellence. Standing in a rebuilt factory in Stuttgart in 1952, watching modern assembly lines produce engines that combined German precision with American production efficiency, Friedrich Weber finally made peace with what he'd learned during the war. His captors had broken his pride, but they'd given him something more valuable in return: understanding. And with understanding came the wisdom to build something better than what had been lost.